Welcome to volumetric analysis. So volumetric analysis is a type of chemical analysis, and just before we go into it, we want to ask ourselves, what is chemical analysis? So chemical analysis can be both qualitative and quantitative. At its heart, it's asking us, can we find out information about this chemical? Remember, qualitative analysis was analysis which is looking at what the identity of the chemical is, and quantitative analysis is looking at the amount or concentration of a chemical that has a known identity, a chemical of known identity. Okay, and remember, we've already looked at a couple of different types of chemical analysis. So in gravimetric analysis, we looked at this in year 11, and that was analysis by what? You analyze the mass of the chemical to give you information about the chemical. Spectroscopy, we analyzed how these chemicals interacted with electromagnetic radiation in order to give us information about the chemicals. And then in chromatography, what we looked at the relative affinity of the chemical to the stationary and mobile phases, and they separated. And based on their separation, we're able to find out information about the chemical. So when we apply the same kind of framework to volumetric analysis, what we see is that volumetric analysis is using volumes of chemicals, right, and measuring volumes of chemicals in order for us to find out information about the chemical. And volumetric analysis is primarily going to be a quantitative analysis technique. Quantitative. So we can usually find out the amount or concentration. Alright, so to understand volumetric analysis, we need to understand the basics of acid-base chemistry. So as a quick revision, remember that acids are proton donors and bases are proton acceptors. Okay, we also need to understand the notion of a weak acid versus a strong acid, and a weak base versus a strong base. So the definition that I'll give you is for a strong acid. So a strong acid is an acid that completely ionizes in water, right? And it readily donates protons. Okay, a weak acid is something that does not completely ionize in water and does not readily donate protons. A strong base is going to be a base that completely ionizes in water and readily accepts protons, whereas a weak base will be something that does not completely ionize in water and does not readily accept protons. Okay, so this is the definition of weak and strong. We also need to know about the concentration. So there you can also have a high or low concentration, right? And we remember that a high concentration of any substance involves what? Involves there is a high number of particles, right? Or a high amount per unit volume. So per unit volume per liter. Okay, so high concentration means there's a lot of this substance per liter. Okay, let's have a look at some examples of strong acids and strong bases. So the strong acids that you need to remember, and the ones that most commonly come up, are hydrochloric acid, HCl, in aqueous solution. In addition, HBr, HI, sulfuric acid, H2SO4, nitric acid, HNO3, and then phosphoric acid. Okay, so this, and this are the most common strong acids you'll see. You then have a look at the strong bases. The strong bases are anything that have hydroxide on them. Whoops, OH minus. Okay, so potassium hydroxide, sodium hydroxide, they are all strong bases. Weak acids are going to be your ethanoic acid. Okay, this is also known as acetic acid. And then HF, ammonium with a NH4 plus, and the sulfuric, the ion here, so hydrogen sulfate ion. Okay, so once you get the sulfuric acid ionizing once, it becomes a weak acid here. And lastly, there's the idea of a weak base, and the weak bases are going to be any carbonates. So commonly calcium carbonate is your limestone or marble, your sulfate ions, ammonia. Yeah, so these ones will be your weak bases. Cool, so the ones that you really want to remember are hydroxide, this one, ammonium, ammonia, and then your carbonates. These are the most common ones that come up. All right, so what's the significance? Let's take a look at HCl. Okay, so let's say I have HCl in a gaseous form. That means that the hydrogen is connected to the chloride ion like this. So the hydrogen is connected to chloride like this, and it's just kind of floating around HCl. So when it's in a gaseous form, it is not an acid, because what happens is that HCl has to be dissolved into a jar or like into some water. So let's say there's water here. When I dissolve HCl into water, what happens is that the H plus is really positive. So it's so positive that the waters around it, so the H2Os around it, remember waters have that delta negative charge here, and there's a delta positive and delta positive. So they are really attracted to the positive hydrogen here. Okay, so the acid looks like this, H plus and Cl minus, right? Well, the H the H is really positive, chloride is very negative, right, in this situation. And that's because the chlorine is a very electronegative atom, so most of the electrons in the covalent bond spend the majority of time near the chlorine. So therefore, it gives chlorine a very strong partial negative charge, and hydrogen a very strong partial positive charge. So when it goes into water, what happens is that the water is really attracted to the hydrogen on one side, so it's so attracted that it splits it apart. But it splits it apart with the electrons staying in the chlorine side. So let's have a look here. HCl is a covalent bond, and the electrons spend most of the time near chlorine because chlorine's very electronegative. This gives chlorine a partial negative charge, hydrogen partial positive charge. When a water comes along and rips that hydrogen off, what happens is it rips it off right like this. So even hydrogen's electron, remember one electron here belongs to hydrogen and one electron here belongs to chlorine, but when water comes along and rips off the hydrogen, it rips it off and hydrogen's electron stays with the chlorine. So what happens is that when I stick the hydrogen into water, we get H plus and Cl minus, because the electrons that used to be shared between them, right, chlorine actually ended up taking the hydrogen's electron. So chlorine gets a full negative charge, hydrogen gets a full positive charge. And remember over here we said that it's this negative part of the water that's very attracted to the hydrogen here. So what happens is that we get the water being really attracted to hydrogen, and what happens is that the hydrogen forms a covalent bond with the oxygen of the water to create what's known as the hydronium ion, which is H3O plus. And remember, the H3O plus has the plus written on the oxygen like that. Okay, so what happens is the hydrogen chloride and the chloride ions will then just dissolve into the water and be surrounded by water molecules. So this process here is known as the ionization. And the idea is that with a strong acid, if I have 100 HCl molecules and I stick them into water, the idea of a strong acid is that virtually 100%, or all 100 of those HCl's will split into the H plus and the Cl minus, and the H plus will immediately become H3O plus. So because of that, we can look at a couple of assumptions. We can say that if I have the concentration of HCl aqueous, right, that's going to be equal to the concentration of H plus ions in the solution, right? Because every single HCl molecule will ionize to form H+, and then that H+ is going to be equal to H3O+. Sorry, it's not equilibrium, aqueous, that's aqueous, my bad. In aqueous solution like this, okay? So if I have a strong acid, the concentration of the strong acid is equal to the concentration of H+ ions, because every molecule of the strong acid ionizes to form an H+ ion, and then the H+ ions immediately react with water to form H3O+ ions, and these are known as the hydronium ions, like this. Now what's the deal with a weak acid? So we said weak acids don't completely ionize in water. What does that mean? Let's say I get some ethanoic acid, CH3COOH, like this. And just a reminder, it's a CH3, C-O-O-H, and this is the hydrogen that gets ionized. So when ethanoic acid reacts with water, all right, what happens is that this is an equilibrium reaction. So not all of the ethanoic acid is converted into the ethanoate ion, right? So in other words, COO minus AQ plus, so this is aqueous, this is liquid, aqueous, and H3O plus. So this is the ionization reaction, right? But the idea is that if I got 100 ethanoic acids here, right, and I stuck them into my solution. So these lines are the ethanoic acids. If I stuck 100 of them into the solution, only a very, very small number, maybe 1 or 2 of them would ionize. The rest of them would actually remain as the unionized form. So this creates a problem, because the concentration of the ethanoic acid, CH3COH, right, is not equal to the concentration of H+ in the solution. Because if I have, let's say, 100 ethanoic acids, only maybe 3 or 4 of them, or 1 or 2 of them, will actually ionize to form H+ or H3O+. So therefore, we see that we would have in the solution, if I looked into the solution of ethanoic acid, right, I would see maybe 100 of these. Well, let's say I'd see maybe 95 of these and only 5 of these. So not all of these things ionize. However, if I were to write out the equation for a strong acid, right? So let's get rid of this and write out the equation for a strong acid. So something like HCl plus water forms what? H3O plus OH. Forms H3O plus Cl minus, like that, right? If I started off with 100 HCl's, right? When the reaction finishes occurring and the ionization finishes occurring inside the jar, if I looked into the jar, I would see 100 of this. So I'd start off with 100 of this, and I get 100 of this. Whereas with a weak acid, I might start off with 100 ethanoic acids, but I'll only get like 3 of these, and in the jar there'll be 97 unionized versions of ethanoic acid in the jar. So this is the idea of a weak acid, whereas the top one is the idea of a strong acid. We also have one more concept that we need to look at, which is the idea of pH. pH is a measure of hydronium concentration, hydronium ion concentration in a solution, okay? And pH is equal to minus log 10 concentration of H3O plus. Okay, there's only a couple of things that you need to know about this, right? The pH, you need to remember first equation here. You need to remember the other equation, which is this: the concentration of OH minus multiplied by the concentration of H3O plus is equal to 10 to the power of minus 14 at 25 degrees Celsius. And the very, very last one that you need to remember is this, or that you can remember, is that the pH plus the pOH equals 14. Okay. The principles that you need to remember about this is that pH is the way of defining pH is that it is a negative log, which means that as H plus concentration goes up, pH goes down. So low pH is more acidic and a high pH is more basic, right? And then as H plus concentration goes down, pH goes up. As the H+ concentration goes down in any solution, the concentration of OH- will go up. And as the H+ concentration goes up in any solution, the concentration of OH- will go down. Our last section deals with how does volumetric analysis work. Okay, so the idea is that you'll have up on top here a big tube known as burette. Okay, and then underneath the burette you will have a flask holding what's known as a conical flask. Inside the conical flask there will be a certain amount of solution. This solution will be known as the aliquot. Okay, so it's a known amount of solution. Okay, sorry, what I meant was that it's a certain amount of solution. You don't necessarily know how much is present. Okay, and with volumetric analysis, it comes to this idea of what we need: three things. We need we need the balanced equation. 2, we will also have a known chemical. And 3, we have to find out information about an unknown chemical. Okay, so for example, let's say in this burette there is hydrochloric acid, and in this conical flask there is sodium hydroxide. Okay, so sodium hydroxide is the base, hydrochloric acid is the acid. First of all, we want to find out what the balanced equation is. The balanced equation will be hydrochloric acid plus sodium hydroxide forms sodium chloride salt plus water. Okay, so we have a fully balanced equation here. The next thing that they will tell you is that they will tell you the concentration of a known chemical, or you will know the concentration of one chemical. So in this case, I'm just going to make it up. I'm going to say that we know the concentration of hydrochloric acid is 0.1 moles per liter. It could be either the thing in the burette, or it could be the thing inside the conical flask, but it just depends on the question itself. But in this example, what I'll do is I'll give you the concentration of this. Then what will happen is that they will give you a known amount of volume of solution. So in this situation, they might say something like this. They might say we had the burette full of hydrochloric acid, and we had a aliquot, or a conical flask, with a bunch of sodium hydroxide in there. They then add enough hydrochloric acid to fully react with the sodium hydroxide. So they add hydrochloric acid into the jar to fully react with all the sodium hydroxide that was present in there. Remember, we said we had a specific amount of sodium hydroxide inside this solution. We just didn't know how much it was. We had a specific but an unknown amount. So sodium hydroxide is our unknown chemical. So hydrochloric acid at 0.1 moles per liter is our known chemical. We titrate, or we add the hydrochloric acid into the conical flask until all the sodium hydroxide is reacted. And once that is done, what we do is we go and we find out and measure the volume of hydrochloric acid that was required to fully react with the sodium hydroxide. So in this case, I might say it took 25 mils of hydrochloric acid to fully react with the sodium hydroxide in there. Okay, so what does this mean? Remember this one equation: N equals C times V. So concentration is 0.1 moles per liter, and volume in this case is going to be 0.025 liters, like that. So once I have the concentration and I have the volume, I can find out the number of moles of hydrochloric acid that was basically dropped into this conical flask. So over here I've got my calculator up, and let's just go ahead and calculate that. So that's going to be 0.1 multiplied by 0.025 gives me 0.0025 moles. So when I get this information here, what have I done? I've measured the volume, right? I get 0.0025 0.0025 moles. So let's go ahead and write that down. 0.0025 moles. So I know that 0.0025 moles of hydrochloric acid was dropped into the conical flask, and 0.0025 moles of acid was required to react with all the sodium hydroxide. So this is where I'll go once I get this information. So let's write that down, 0.0025 mole. Once we write this down, what we realize is that this amount of hydrochloric acid was required to fully react with the sodium hydroxide according to this equation. This equation says there's a 1-to-1 ratio between hydrochloric acid and sodium hydroxide, which means what? Which means there must have been 0.0025 moles of sodium hydroxide in this jar. And there we have it. If you then measure the volume, you could then find the concentration. Remember, N equals C times V. So we know that there was 0.0025 moles, and we know the volume. Let's say the volume was like 50 mils, for example. Then we can find out the concentration by dividing this by 0.05 to get the concentration in moles per liter. Okay, so that's a quick introduction to volumetric analysis. We have balance equation, we have a known chemical, a chemical of known concentration, and we have an unknown chemical, a chemical of unknown concentration, right? So I'll just write that, known concentration and unknown concentration, okay? And through the reaction and measuring a volume, we can find out the amount or concentration of another chemical.